Hello everyone, in this video I'm going to be talking about a method for contraband material detection in package security screening. And this is a talk in ICMLA 2021, and this is a joint work of myself and my supervisor, Professor Breckon from Department of Computer Science at Durham University. A few words about the background. This work arises from a real-world application in airports. When you go to airport before boarding, your bags and suitcases need to pass through an X-ray machine as shown in the image. The machine scans your baggage and generates an image like those shown at the bottom. Human operators then use their expertise to find out any potential prohibited items in the image. Currently, 2D X-ray machines are deployed in most airports across the world. In our previous work, we have developed automatic algorithms for prohibited item detection in 2D X-ray images and achieved high performance. However, prior works only focused on the prohibited items with specific shapes, such as firearms, knives, and so on. Other than these prohibited items, contraband materials, which can be made into explosive devices, are also important targets to detect from baggage in security screening. Our work in this paper was motivated by 2 points. So first of all, contraband materials detection using 3D CT imagery is a challenging task. Firstly, as we have mentioned, the contraband materials can be of any arbitrary shapes which are determined by the containers. As a result, these appearance features are no more useful for material detection. So it is usually formulated as a segmentation problem rather than a detection problem. We aim at investigating two types of techniques for 3D segmentation. One is based on the 3D convolutional neural networks, and the other is based on the point cloud processing. We'd like to know how different settings affect the detection accuracy and the computation efficiency. And also we need to consider the computational cost when we try to deploy the algorithm to the actual CT machines, like the GPU memory and also the training time. Before going into the details of our method in this work, I'd like to talk about some related work we have done in the last couple of years. We applied 3D object detection algorithms for threat item detection in 3D CT volumes for baggage security screening in airports. 3D bounding boxes are predicted by 3D convolutional neural networks given the baggage CT volumes as the input. This has been proved to be effective in detecting threat items with specific shape characteristics like handguns and knives. For contraband material detection, we proposed a morphological operation-based approach for 3D segmentation, which is followed by a classifier like SVM for detection. However, in this work, we will use more advanced deep neural networks for material segmentation and detection in 3D CT baggage imagery. Here is the pipeline of our method. Given a 3D CT volume containing benign materials as well as contraband materials, we apply two types of 3D segmentation methods to segment the contraband materials. As a result, each voxel of the 3D volumes will be assigned with the predicted material label. The segmentation results can be inaccurate in the voxel level. For example, there could be holes in the objects or isolated false positive voxels in the segmentation results. To retrieve the contraband materials, we apply post-processing to the segmentation results and get the final detection results from which we can understand what kind of contraband materials are detected in the baggage and their shapes, volumes, and locations. Our work focused on the investigation of two types of 3D segmentation methods, 3D CNN-based UNet and PointNet for point cloud data processing. In the following slides, we will describe each part in the pipeline. The first type of 3D segmentation algorithm we're going to use in this paper is UNet. UNet is a typical CNN architecture for image segmentation. It can be easily extended from 2D to 3D by replacing the 2D convolution with 3D convolution. As we can see in the figure, a 3D UNet is composed of a contraction path in the left-hand side and an unexpected path in the right-hand side. The contraction path is composed of a sequence of downsampling modules. Each level, the downsampling module downsamples 3D feature volumes by a factor of 2 in all 3 dimensions, x, y, and z. The number of feature volumes in different levels can be specified as required. To be noted, the feature volumes are all 3D volumes. For example, in level 0, there are 32 3D feature volumes in contrast to 2D feature maps in 2D CM models. The expanding path is composed of a sequence of upsampling modules. In each level, the feature volumes are concatenated with the corresponding feature volumes from the contraction path. The detailed components of each downsampling module is illustrated in the diagram. For 3D UNet, we have a pooling layer, a 3D convolutional layer, followed by a ReLU and a batch norm layer. Another 3D convolutional layer, followed by a ReLU and a batch norm layer. For the residual 3D UNet, we have three 3D convolutional layers and a skip connection, and that's why it is called residual 3D UNet. Similarly, the details of the upsampling modules can be found in the diagrams on the right side. The second type of 3D segmentation used in our work is the point cloud based methods. So for baggage city volumes, there are usually large regions of non-thread voxels which can be easily recognized by simple thresholding based on the prior knowledge. As a result, the voxels of interest are actually sparse in the 3D city volumes. Using 3D CNN-based model could be inefficient to process such sparse 3D city volumes. We can convert the sparse city volumes into point clouds by considering only the voxels of interest. Then we can use the popular point cloud processing methods like PointNet and PointNet++. The basic idea of PointNet is to extract the pointwise features from the point clouds and then apply a MLP to predict the pointwise labels. PointNet++ is an extension of PointNet with improved performance. For more details of PointNet and PointNet++, we refer the readers to the two references in this slide. The segmentation results give the voxel-wise class labels, which can be inaccurate. The post-processing aims at predicting the materials based on such predictions. For each class C, we apply a series of morphological operations, including dilation, erosion, and connected component leveling. The set of detected objects are finally pruned by the threads of volume. For example, we will remove the detected objects whose volumes are too small. To evaluate the effectiveness of the proposed methods, we do experiments on a public dataset, NUATR, which contains 3 material signatures, saline, rubber, and clay. We use 94 city volumes for training and 94 for testing. The intersection over union metric is used for the evaluation of different segmentation algorithms, and also the precision recall F1 are also used. For the detection results, we use probability of detection and probability of false alarms as the metrics. Okay, in the first experiment, we investigate different 3D segmentation algorithms, including point cloud-based methods and 3D UNet-based methods. And more importantly, we investigated the effect of different values of the hyperparameters, like the number of levels for 3D unit and the number of feature volumes in the first level of the for the 3D unit, and also the factor. This is actually the downsampling factor. We apply a pre-processing of downsampling the original city volumes so that it can fit into the GPU memory we have at hand. So the factor, the downsampling factor we use include 2, 4, and 8. So we report the results, segmentation results, in terms of IOU for the background and 3 different materials, and also the overall results. So the results in this table can give us some insight. So first of all, we can see clearly that the first 4 rows, PointNet and PointNet++ given generally worse results and the 3D than the 3D unit methods, but it's not completely rubbish. For example, PointNet++ can give reasonably good results when the downsampling factor is equal to 2. But we can also see that if we downsample the city volumes by a factor of 4, the performance degrades to some extent for both PointNet++ and PointNet. And for 3D unit, when we downsample the city volumes by a factor of 2, we got the best results with the overall IOU of 74.5. And if we downsample the city volume further with a factor of 4, we get a slightly worse result. And further downsampling the city volumes by a factor of 8, we get a significant performance drop here. And then we try to use a large number of feature volumes for the 64, and the performance can be actually improved. And then we use 6 levels, and with these 2 combinations we can get very good results. And for residual 3D unit, we can actually get very good results for these 4 different combinations. But it's the best result is still 74.9, which is comparable with our best 3D unit performance. So in summary, we have better performance of from UNet than point cloud based methods, and also we should use different hyperparameter combinations to get the best results. In this table, we present more results of different segmentation methods. We report precision recall and F1 score, and we can see that the results are consistent with what we have seen in the previous slide. Then we apply the post-processing to the segmentation results and get the final detection results. So to evaluate the final detection performance, we use the metrics of probability of detection PD and the probability of false alarms PFA. So in this table, we also compare our different methods investigated in this paper with the SVM-based method proposed in this reference. So this is quite interesting. So actually, if we focus on the overall PD, you can see that the .NET++ can actually achieve a very high overall PD, although the segmentation results are not that good compared with other methods like 3D UNet. But the problem is the PFA is also very high, so we don't want the higher PFA, which will this will cause unnecessary work for the operators in the airport. But the 3D UNet and the residual UNet can give very good results of high probability of detection and a very low probability of false alarms. It depends on your combinations of the hyperparameters, so you can have a trade-off between a PD and a PFA. So overall, the results of 3D UNet and 3D residual UNet can be very appealing, as we can see in this table. And also you can have different trade-offs by tuning the hyperparameters. And lastly, we compare the investigated models in terms of their complexity. So we report the number of parameters and also the flops of different combinations. So we can see that .NET and the .NET++ have, especially .NET++, has very few parameters compared with other models, and also the .NET++ have fewer flops than others. And for 3D UNet, actually, when the number of levels is not very high, when it is equal to 4, the number of parameters is not that high, and also the flops is it's acceptable, as we can see here, when the factor is the sampling factor is 8. But if we still remember that the best performance achieved by 3D UNet is with this combination. And here actually you can see the number of parameters is very high and the number of flops is also very high. And so we may also consider the model complexity when we deploy the actual algorithm to the CT scanning machine. So this is also very important information to consider, together with the performance we reported in the previous slides. And finally, this is a qualitative evaluation of different models. And in this figure, in the first column in the left side, we showed the original CT volumes. We have A, B, C, D, E, 5 different CT volumes for examples. And in the second column, we showed the ground truth segmentation or detection results of different materials. We have 3 contraband materials which are represented by different colors: orange, yellow, and blue. And then in the last 2 columns, we present the detection results of two models, PointNet++ and 3D-UNet. So we can actually see that the qualitative result is consistent with what we have seen in the tables. Okay, to conclude, so 3D-UNet is effective in contraband material detection within 3D CT package imagery, and point cloud-based methods it's not that good, but can be alternative solutions given the merits of low computational complexity.